Еще раз всем привет, кого не видели. Сейчас у нас будет доклад Дэвида Паси, который приехал к нам из Польши. Если спросить Дэвида, кто он ответит, что он борец за качество и улучшатель жизненного цикла программного обеспечения. Вот. И сейчас Дэвид нам на практике покажет, как он это делает. Он возьмет 3 примера и покажет возможные тестовые решения для этих примеров с возможными проблемами и тем, как эти примеры, как его решения можно внедрить в жизнь.
Okay, so that's me now. Okay. Yes, Polish. Okay, yeah, cool. That's so many of you. Usually, I like embedded tracks. It's just 20 or 30 people. Half of them do not understand anything. But I promise I will do my best to let you understand at least something. Yeah, so just to not waste the time, let me quickly introduce myself. That's me, Dawid. I'm from Krakow. I live in Kyiv now. And working in PetCube, it's like Kyiv startup, so probably some of you may know. And we set up Ukraine QA meeting, so maybe you can recognize somehow. If not, you should surely join the group. Yeah, now I live in Kyiv, as I said, and like about my passions, I think because we have how it's called. Let's have it in English. After party later, so you can ask me what do I like. I will show you one thing, and that's what I like here. It's kind of, let's call it reverse engineering in software context. When you translate my first and second name to Cyrillic, it's still Dawid Pacia. I don't know if it's correct, but when you revert it, it's Dawid Pacia. So it's no more Dawid Pacia, it's Dawid Pacia. So whatever you call David, it's fine. Okay, so let's start with examples. I have 3 kind of projects without getting deep into technical details to let you understand how the world of embedded, even if world of embedded looks very narrow for most people working in web or mobile, it's not. And by those 3 projects, I will show you how it can differ on a different levels. So let's start with the first one. The first one relates to smart home. We have main board for smart system, for smart, let's call it server, and it's fully embedded. And we want to test it from the customer perspective and test it as a black box. So check all inputs, outputs, if USB ports are working, and so on. What do we really want to check? This is our device under test. And first question, who of you work, I should ask like 2 minutes earlier, who of you is working or have been working with hardware-related IoT companies, and so on? Okay, 5, cool. So for you, probably it will be more interesting about technical details. For other, I will try to explain as simple as I can. We have all components that customer can intentionally or not intentionally use somehow. So, for example, LED or buzzer or USB ports is trivial. But what about those protocols like I2C or AJ12? It's called Lego, and so on. Another question, what do you think from those 12 is like, number 1 is blocker to start testing? Which of those components is most crucial in testing? Exactly, yeah, but you do not count. I won't ask you anymore. Yeah, definitely, because you need to somehow communicate to this device and then operate on that, like on normal Linux or kernel system. So we have this device under test. We need another device to execute tests, and the best way is to use any other embedded platforms to control it. So I choose 3 of them. The most popular, it's Arduino, this Raspberry Pi on the right, so you could hear about it, and it's BeagleBone Black. What do you think is the most suitable for that case? You can guess. Which one? Or you can keep silent. Okay, who vote 1? No one. Who vote 2? So everyone vote 3. Cool. But it's not the correct decision because actually every one of them choose perfectly. From my perspective, from QA perspective, I just need a limited number of inputs and outputs, and usually that platform has much more. So I would say even more. For that case, the best choice is the cheapest choice. So it doesn't matter which one you choose, just need to meet your requirements. And this is like the platform we choose. It looks scary, a lot of inputs, outputs, but what really matters is here. So we have like this input and outputs. We have a number of ports that we can set 1-0 binary signals, for example, to turn on LED or to reset button and so on. We have somewhere here power supply and so on. And on the right side, you can see the full equipment that we need to set up this environment. Looks very minimalistic. So that's my point. If you are not hardware engineers, even if you work with hardware parts, you work very hardware devices, you just need elementary knowledge or even no knowledge because there will be always someone who can help you. So by that, like 3 LED lamps and so on is totally okay. Now very technical part. And I want to show you how important it is to think about structure, think about architecture. I think not only here, but in every area of testing, how important it is to make it well structured, to build proper architecture. So let me start from the bottom without showing code. The first thing is config. So all numbers of all USB ports, LEDs, all GPIOs, and so on, to keep it in one place. Sounds similar, yeah? All the configuration in one file. It's trivial, but if you won't do that, that's painful. Then we have UART. So what is your name? Andy. What Andy said, he's a cool guy, he knows a lot. To send like the simplest comment via UART. Send open UART, open communication protocol, send something. Maybe write data or reset, and so on. Then we have this part, and it's like the higher level of abstraction that can operate like the kind of functionalities. So we can clear our LED state or say something to the device to push some signals like you can write in Linux command, whatever, date or ls, and so on. And last thing are supporting files, and it's probably the most unique in embedded. Because if you want, for example, check memory, it's the best to send a big file and check if it was stored, then pull this file and check if it's working. So that's kind of memory check. Another thing, how to check buzzer. Probably you won't check buzzer working in web components. But here it's pretty simple. You send and you can turn whatever. Santa Claus is coming to town. That's cool example. And play it on this board. The same with LED and so on. And of course, everything we know well, logs and tests. And here I do not have tests written in BDD way, but there is definitely no problem to put one more layer of abstraction and wear it into BDD. Let's implement something in that case. So by 7 lines, we have full coverage of one of those interfaces for the customer. It's LED. So you have LED like in a phone, indicating something or whatever. What to do? To get instance, so to run our engine, and then login is understandable in that way because we added higher level of abstraction. Then we say something to device and get kind of assertion, expecting if from the software layer we get the same. So we said something, get a response, check if that's the same. And then just clear buffer to have the next test case like fully ready for the testing. And then just waiting for any input. It can be, and that's interesting because you can fully automate it, but recognizing LED is kind of technical job. But you can do it semi-automatically. So just put the button and waiting until your intern is like helping you or whatever. Okay, so we did it. We have 7 steps. We have implemented 1 test for LED. And as you see, without getting deep into code, we have covered one of 12 components. And actually, at the beginning, the project looked very scary. So start thinking from the top, start thinking from the very big picture, and then getting deep into details. OK, but we are QAs, so we know that there is always some problem. That's the rule. Yeah, fix something and there's another problem. In our case, it was self-resetting NAND flash. What is the problem? It's the whole memory. If you store something, you lose everything. It's good if you find it in the development phase or R&D phase, but not after the project is sent already to the customer. So what can be done in that case? The problem in embedded, those tests or problems are very flaky. Do you know description flaky tests? Who doesn't know? OK, cool, so I can explain. False negative and false positives probably are better known, so it gives you like correct result when it should be false, and in the opposite direction. So it gives you false when it should be true. Flaky tests is like kind of something bad, because it can give you randomly chosen results. So under the same conditions, in a different executions, it can give you either false or true. And it's totally random. It's undeterministic. In embedded, it's pretty common. So that's why it's so tough to investigate it, and usually it can take you up to a few days, weeks, sometimes months. In that case, that was just 3 months. And it's kind of automation. So the best way is to run it in the cycles. Here was just a specific case, but you can implement it in any other. So it was checking memory, like putting new image and then deleting, putting and deleting. What happened after like 30,000 of iteration, we found out it was like electrostatic discharge. It is the same when you touch something and then it kicks you, like the table or some electronics. You know that? It hurts. And yeah, as I said, it caused resetting flash memory. But the second issue that we didn't realize was I2C bus communication protocol. Someone knows what is it? What the heck is it? Unless you. OK, so without details, it is responsible, for example, for real-time clock. Real-time clock, so clock. Just imagine, it looks like unnecessary protocol, but in smart home, when it stops working and you have scheduled some events, for example, you leave your home, you go to work, all lockers are closed, all doors are closed, and so on. But if that's not working, then behavior can be random. And just imagine the thief that wants to rob you. He comes, and then he has randomly opened doors. Yeah, it's like surprise. OK, so we found the bug, we implemented, and that's the big picture, how testing of embedded platform can look like. Let's move further. The second project, and the project is quite different. Who works with wireless communication? Somehow use Bluetooth or Wi-Fi. Somehow. In mobile, probably. Most of you use Wi-Fi or Bluetooth. So we want to build fully isolated environment to check functionalities in the clear way, in the clear environment. So sending, receiving signals, packets, and so on. And again, let's start with requirements. So it has to be definitely resistant to do not get any packets outside. And maybe some of you know, but Bluetooth and Wi-Fi works on the same frequency. You know which one, like 2.4. Yeah. So if you have a lot of Bluetooth communication and wireless communication, it can interfere a lot, and then your connectivity issues can occur, and you do not even realize. And that's the problem at the companies working with a lot of mobile devices. So the same here. It should be fully isolated to check pure functionality. Then remote access, which is to put it somehow into continuous integration environment. Dirty cheap, because everything is in the context of startup. Modularity and simplicity, that's pretty common known, like his rule. Okay, how to start? So we want to build that fully isolated environment. The first thing surely will be to build kind of box or cage to somehow isolate it from external packets. And it was called Pamela 2.0 box. The story is pretty simple. The first iteration was with box after chocolates, and there was Pamela Anderson on the cover. And then the professional one was called Pamela 2.0. The second one is wireless flasher. So we have this box, and we have devices inside, but we don't want to take them off every time, but put the new firmware. Firmware is like the software on the embedded devices, and then using this flasher, start our testing with always new image. So when the image is built after development, then you can start testing. And the last one is integration. Who knows what is BOM? Okay, that's better. So it's like listed items that we need to build something, build product or build board. Like in the case of like my current company, it's not, but let's imagine for camera with laser for cats, our BOM would be like a bunch of resistors, CPU, plastic cover, and so on. So this is like BOM for our isolated environment. What is here important? That all of them you can find in a shop, like quite easily, and it's quite cheap. At the same time, already done solutions are pretty expensive. That can cost up to a few thousand of euros. So that's why actually we decided to build it on our own. How does it can look like? So let's start with the top. On it, here you have strength of signal, and here is like the development phase. Here, till now, it looks pretty solid, and here starts like fun with foil, and here more foil. Good lesson for me from that, those wires always transform the signals through wires, which can be pretty problematic. But at the end, you see, it's almost no visible. And the result was that pretty nice silver cage. Oh no, it's here. Silver cage is true engineering job. But we have no signal, and our test sent like 380 million packets, and there was not even a single one received. So I encourage you to experiment and to try to build on your own, and then during the development you can understand the protocols you are working with. But that was just one thing. The second is to implement our wireless flasher, so to have it always ready to put into continuous integration. Just once again, imagine simple flow. You have developers, like firmware developers. The average age of firmware developers is much higher than probably you can expect. And it's like quite tough to build it into CI. And that's why we need something that will flash it all the time after it's done, after it's built. So it's like the general architecture, and everything here is inside silver box, so you can skip it. Here we have just central station to control and FTP server to communicate and maybe store data somewhere further. So first step number one. We should understand what we want to do on those devices, which operations. The simplest one, because then you can implement it somehow. You can easily implement it. For example, erase something that is inside device. It means like you uninstall mobile application on the device. It's the same, just remove image on this embedded platform. Reset platform or just read something. And this is a nice wall of code for those who are quite familiar with Bash. For those who work with hardware, it's totally not important. important thing is here. So what is important? Even if it's tough to implement, even if you have just one guy who can write such scripts, it's important to somehow control, to encourage him to give you simple response. So what I want to respond from that? I want to get a list of devices with MAC addresses versus port. Port means USB name. And this is my output. It's pretty simple JSON file. I know for that port I have this MAC, for that this one. Here is nothing, and here is something strange. Maybe it's locked, or just someone hide it. So we have first step. We have scripts and simple output that we can receive to process further. Now, time to put firmware every time after it's done. How to do that? Well, as free, maybe some other storage place, then just download it, and in 3 lines of code, we can put it to our device. So one line of code is to pull image, the second is to push it to the device. Once again, you can compare it to mobile devices. You pull APK and then using, for example, for Android ADB, push it to the device. Just 2 or 3 lines of code. The third step, and this is what can be useful for less technical person, is to build higher level of abstraction again. Get hex list, maybe it's not very clear, but then we want to check if it's downloaded. We want to check if you have the newest one. When you put it later as a step in test suite, that's pretty understandable. The same here, flash list of ports. So we put firmware into every device, every chosen device. And this is step number 3. Step number 4, implementation. And again, 3 lines of code just to implement it fully. So we have just instance creation. And then using this higher level of abstraction, I hope everyone can understand that we have this instance, and then we pass list of MACs to flash. Somehow clear, more or less from the big perspective? OK. If at least one person can understand, that's good. Unless you are technical. OK, this is like, I lost voice. This is integration part. So you see here is like our isolated platform, and this is fully opened. And actually, this is how it looks like. You have something to control, then flashing devices, and then boards. And it's done. So we have full communication with devices, sending, receiving something, flashing, and so on. And we have isolated environment. So totally separate activities, like build your cage and then implementation. And that, once again, is good to start with big concept, how to start implementing it, because I believe at the beginning it was, again, quite tough project to understand and quite complicated. Even now, it's quite complicated. Good. And the third project, I think the simplest one, and there is no code, fortunately. You can smile. So the case here is we want to identify the real behavior of bulb. So this is bulb. And imagine we have RGB, so 3-colored bulb. We control it via mobile application, then change color, and then want to check the real behavior. It was really verified. Of course, the last step is to put it into continuous integration environment. To every time when the firmware is new, then using mobile application, change the color, and then check if the color was changed. Simple. And it's described here. OK, to visualize the process, we have application, we have current state, we change the color, and we have this state. It's nice technology. You can create your own private spaces in the cellar. You can change colors. You can differentiate. You can change them. But the testing process is quite challenging here. So what would you use to verify it? what kind of tool, technique, what kind of approach to check real behavior, except for eyes. Okay, who use camera? Sometimes, cool. So definitely, what can exchange your eyes? It's camera or any other tool capturing pictures. And this is how it was done. And for me, that was the flow, the whole flow. So I have the camera, I see like, let's say we have 9 bulbs. I take matrix, and then I have 9 values, and get the response. And this is the real flow. The real flow with all processing, with something I didn't predict before. But what is important here, it's not a rocket science. It's definitely not rocket science. And on the level that you want to check real behavior of your device, the image processing is pretty simple. I can give you another example why it can be useful. Now, in my previous company, you have device launching treats. So it's like launching treats means you have cookies for pets. It's like then into chamber, and then they are flying somewhere. And again, if you want to put into your continuous integration, you need to somehow verify them. You can, again, look with your eyes or employ your dog or cat, but the best way is to put camera and track again. The same example here, and there are many other examples in embedded world when you can just use it. So it wasn't that simple, but it wasn't also that hard, as you can see now. So again, let's start step by step. And because of that requirement, again, it's in a startup context, so it must be cheap. Who works in startup or small companies? Any startup guys? No startup guys? So you won't understand it. But just believe me, costs are crucial. So you have limited budget, that's always. You can spend it to the real tool, or somehow you use it into your own purpose. What are the requirements? So definitely unchangeable conditions. You have bulbs, you have vision system, and you have day, you have night. You want to change this, you want to always have day, but you cannot. If you can, just tell me, that would be cool. But what is important when it's a day, you have a lot of influence from external sources. You have sun, and it will change a lot your image. So here, it's important to somehow isolate environment, and you can call it laboratory. So what we did was kind of camera here, and just matrix with bulbs, and then really professional one, put the hood, black hood on that. So now it's isolated. We have matrix with bulbs, we control them from somewhere there is mobile phone controlling, and we have this environment. And this is image from the inside. It's already after like implementation. It was Python and OpenCV, so we have 9 squares and bulbs here. And now processing it is extremely simple. You can just choose even either the average value from the top or filter something. It depends on your skills. But on a basic level, it's really not a problem. Click. One pro tip, or just tip, be careful about configuration values, because every camera, like cheap camera, connected to notebook wants to use automation configuration. So it's worth to disable it and always set it on your own, because that's what can break your test. And then you will have false negatives or false positives. Just example here is just one parameter, and here is definitely good values, and here are not. So the point from this slide is be careful about configuration. Some image processing, you saw that picture is the real image from the camera, this closed camera. Then after very simple processing, you remove everything around and you get some like fuzzy circles. And then the output is like that. So you have 3 values, RGB scale, And you have RGB scale also here. And now it looks quite similar. You get some values, and you want to put them into the proper range. So we have that kind of control. And we have values from our bulb, like 3 numbers. What we can do with those 3 numbers, we can put it somewhere on this chart. To not make it very simple, it's not RGB scale, it's color temperature. So probably when you buy bulbs, you can buy warm or cold bulb. You know that. And this is how it looks like. Here, the color is described in, I think it's Kelvin or something. But the most tough thing is that you cannot directly put your 3 values here because it's not linear. But use your basic technique from ISTQB foundation level. Try to place it into, try to split it into ranges, and then put those values somewhere between those. And this one is definitely somewhere here. So we can describe if it was good or bad, and we do not depend on the small conditions outside. So we have values, we can place them, voila. And now, why you should care about it? So why did you come here? That's the main question. Because you wanted to listen about 3 project examples. But what I want to show you is that even those 3 projects that directly do not touch you, they somehow influence you just by 1 example. This is the table with mobile phones. This is when you send packets, it can be Wi-Fi or Bluetooth. You can send it in a proper frequency. So, for example, during the time, like 4,000 packets were sniffed by a tool. And another one is the number of packets in noisy environment. So we take them off like from this cage, we make a noise in the environment, a lot of packets, a lot of devices connected to Wi-Fi, and so on, and compare them. As you can see, the difference between the best one and the worst one, it's not like advertisement for Galaxy Tab and not advertisement for Sony Xperia, but it's what you can experience not working in embedded, just working with mobile phones. And even if you check models, for example, for some of those phones, the Bluetooth module, as I remember, for this Galaxy and one of those Samsungs is exactly the same. And what? And nothing. It's like 5 times worse for one devices, because there is always something else than just Bluetooth module. Then can be, like I showed you at the first project, that can be different firmware because the company developed it in a different way. So hardware is the same, but the firmware inside is different. And then the difference in reliability is huge. So that's to remember for the future. Now, takeaways. No technical takeaways, but modularity here. We always broke down those components into small components, even inside one project. So we have platform, embedded platform. We broke into single features, single components, then communication level, and then simple comments. The same with this last one. So we split into vision system, then implementation, and a separate part as building this like hood to put it under camera. And even more important is that you can use every of those components of something I called project as a one brick, one part in your continuous integration system. Just imagine, you have this board, and it's like kind of your prototype, but just add some bulbs on that. So first thing, you check hardware. Then the next step in your continuous integration can be validation of communication, so the second project. And the third can be just verifying if the real behavior from mobile application is correct. But it's not true. I mean, it's not true we did it, but it's like just my imagination, how it can work. But definitely every of those components were put into continuous integration, especially the last one. You see, you have hardware and you have mobile application. Yeah, looks like integration. So it was integration level test. Then think big, but act small. You have big picture, and like with this architecture, it's much better to start with thinking instead of, like, it's pretty normal for developers, for automation engineers. So code first. I see the task, I start coding. After 5 days, was 5 days less in my next planning because I wasted somehow. But instead, you can spend 2 or 3 days like having brainstorming sessions or whatever, and just talking with your friends, maybe among like some clever idea, okay. Never mind. I wanted to say that most of ideas are stupid and just some are smart. I hope that's not true, but you know, that's reality. Iterate and refine sounds like pure agile. Iteration, refining, yeah, that's true. Even more, because you saw a lot of tries, even with this box, a lot of iteration, a lot of improvement, and it's much better than doing everything at once. The same with building code for embedded. And, oh, I must say that. Unleash team creativity. So again, you have thousands of stupid ideas, and you have one tester who has a great idea, and it will help you to improve, to speed up your testing. So I believe in embedded, which is not very popular, so that's very cool you came here. It's not popular, so probably if you have 10 testers, maybe one or two of them has experience with embedded. So probably everyone starts like from the bottom. But maybe there is someone who has like very clever idea, and let's do it this way. Why not? So I really encourage you to make brainstorming sessions with your teams. If you have something uncommon, some uncommon problems, it's not related only to embedded, probably to different areas as well, but most of web parts are quite well known. But for example, connectivity issues. Then continuous integration in hardware. Yeah, it's not just possible. For me, it's the only way to deliver product fast. So IoT companies usually are quite small companies, and the speed you deliver your product on the market, so time to market value, is crucial. Without continuous integration, your deployment cycle can take up to 1 month, because you have firmware development and building, and then at the end there is somewhere tester doing manual tests, and then it's getting back. By building continuous integration, you can decrease it even much more than in web related projects or mobile related. IoT is hardware, hardware is physics, and physics is not very pleasant sometimes, like these electrostatic discharge. So you don't have to know physics. Who likes physics? Oh, less people than working. That's pretty cool, because two people like physics and 5 people work in hardware-related companies. Okay, so just to realize that there is physics, and you can have problems that are unknown, and it can relate to just physics, and you can do nothing unless to understand how to do it and fix something. Just for this electrostatic discharge, you can use humidifier, so to increase steam value in the air, because the air can be too dry. That's a very simple solution, but it can take a lot of time to investigate. And the last thing, hardware is fun. I don't know if you believe me at that stage, but that's my opinion, that hardware can be real fun, and when you start doing it on your own, even building like smart home platforms, that's really cool. You can put it in some places, you can put it in your own home, and so on. The last project I have seen, because I'm like cat lover, and it was like the guy living in a village in US, and he had a cat, like half wild cat. So When he wanted to sleep at home, he slept at home. When he wanted to get out, he got out like cats, like every cat. And when he get back to home, there was a vision system to recognize cat's face, and the guy just saw in mobile app on Slack, I am here. And then he made an improvement, and there was smart locks, so when the face was recognized, it was unlocked, and the cat came in, and if there was another cat, it was closed. So yeah, hardware is fun, you see. So yeah, that's everything from my side. You can find me here, or in Ukraine QA, or Ukrainka. I call it Ukrainka. Thank you.